This is your online module on the normal distribution. At the end of this module, you will be able to identify the characteristics of the normal distribution and calculate probabilities based on a normal distribution. The three characteristics that you need to remember about the normal distribution is that it's a unimodal, symmetric, and bell-shaped curve. Even though many variables are nearly normal in nature, none of them are exactly normal. Remember, this is also a model that we are using. Therefore, it's not perfect, but it's really, really good for many phenomena. Therefore, we keep using it. And in my opinion, I consider this as the queen of distributions because of the level of use that we make it. And it's denoted by n in parentheses mu and sigma, which basically reads normal with mean mu and standard deviation sigma. So let's see an example. In this example, we have the distribution of heights of the US population around males. And then a dotted line with the heights of males that are reported in OkCupid, which is an online dating site. So from there, from that dotted distribution, which is observed, we create a model, which is the one that is solid, and we see that there is a shift. What this says is basically that males in OkCupid report to be a little bit higher than they really are. But what about females? Well, the shift of their distribution is actually similar. So basically, we see the same trends across both genders in online websites, in dating websites. So this came from an article from some time ago, but those are kind of like the type of insights that normal distributions can give us, and how different behaviors and shifts and centers can say. So going back to their characteristics, let's remember that the main things that we care about the normal distribution is its mean and standard deviation. So if we have two normal distributions, the first one centered at 0 and with standard deviation equal 1, and another one with mu 19 and sigma equals 4, then we can draw the following plots. And as you can see, they look the same, but you can observe, right, like the center is what they should, and the unit for each standard deviation actually follows what they say, right? So but we basically use this type of representation for practicality, because if we actually put it in the same scale, then they will look something like this. This one will be really peaked and narrow, the other one will be really short and flat. So we will need a certain mathematical modeling for each of them. Therefore, instead of going that route, we stick to this representation for all of them, and we try to just map those scales and units into the same as a standard normal. So what does this mean? In order to make this scaling, what we are doing is standardizing whatever we have and creating a centered score around 0 with the standard deviation 1. So this is called z-scores, and they are calculated by each observation that I have minus the mean over the standard deviation. So the z-scores can be defined for any distribution of any shape, and then we use that to calculate percentiles. So we're going to talk about percentiles in a second. Observations that are more than 2 the standard deviations away from the mean, or have a z-score absolute value greater than 2, then are usually considered unusual, and this is a powerful insight, and we will see why. So a percentile is basically the percentage of observations that fall below a given data point. So for example, let's imagine that gray area actually contains 75% of my data. Let's say that so that will say that 1800 is actually my 75th percentile, or Q3, for this distribution. So I would need to, but if I have something else, right? So let's say that I want to calculate how much percentage of observations I do of my distribution falls up or below 2100, right? So I will actually need to make a calculation. So for that, I will use R using pnorm. So for example, let's say that I give the actual threshold value that I originally gave, 1800, with this mean or standard deviation 300. We can also go the other route and use mean 0 and standard deviation 1 with a normalization of 1800 minus the mean over the standard deviation of that population, of that group. So this is the calculation. You're also welcome to explore applets like the one indicated here, although this one requires Java for you to actually use it. And the other route that you have, of course, is the use of tables. How do we use tables, actually? So once you have a z-score, like in the previous example, we had let's say we have a z-score of 1.00, then this in these columns, we identify first the integer and the first decimal, and then the columns have the second decimal. So if we sum up, my row value and my column value is 1.00. So the intersection of those columns will give me the percentage of probability that is contained up to that point. So that is how these tables are read. So moving forward in terms of applications of the normal distribution, something important for you to know as an engineer is the concept of Six Sigma. A Six Sigma process basically it's shooting for, instead of having 3 standard deviations in their specificities, in their specific limits, they have 6. So that will mean that instead of actually allowing yourself to be out of control or having observations that are really far from where you want them to be, have them to be even more rare, then this would put your process in a really tight control. So this basically tells like you will have one defect in a process every million or billion, I don't remember the calculation, it's actually here. So if you are interested in going to industry, I certainly encourage you to dive deeper into this topic. We won't be covering it, but I definitely wanted to talk about this for calling your attention to it. Other elements that you will probably find in industry is statistical quality control or process control, in which the distribution or certain processes are understood, limits are established. So for example, you can see here the upper limit and then the lower limit. And once a process is out of the limit, then actions need to be taken place, right? So it might range from looking at the potential problems in the line, or even stopping the line until the problem is fixed, because if it's something really critical, then it's really important that you don't allow that process to go out of control. So the normal distribution has particular characteristics that make it powerful in the sense of knowing which proportion of data you're going to contain in between certain spaces. So for example, within one standard deviation, you can say that there is 68% of your data, and within 2 standard deviation, there is 95% of your data. And that's why we say that outside of those limits, the observations might look already unusual a bit. And then 99.7% of your data should fall within 3 standard deviations. So, you know, like 0.3% of your observations should be, it's okay that those will be out of control. But even with that, you know, you will pay attention, say like, oh, this is maybe an outlier, and why is that, etc., etc. So if you have observations that fall way beyond that, like 4 or 5 standard deviations away, then you definitely need to pay attention to them. So let's say in this example that we have a distribution that is nearly normal with mean 1500 and a standard deviation 300 of SAT scores at some school. So we can say, based on the previous rule that we described, that 68% of the students will score within 1200 and 1800. Then 95% will be in between 900 and 2100. and 99.7% of students score between 600 and 2400. So when we try to check for normality, there is this other thing that is called a normal probability plot. We won't be building it from scratch in this course, but basically the rationale for this is, imagine that you order all your observations from the smaller to the largest in a cumulative fashion, right? So the observations keep piling to each other. Then you calculate the probability that that observation will be observed if you have a normal probability. Therefore, this line represents a normal density, and the dots represent that cumulative distribution. So if those lines, if those dots adjust to that straight line, then it is a normal distribution. But if it's really deviated from it, like if you have a strong tail or such, then you probably won't be that confident that it's a normal distribution. So let's do an example here. Let's say that you work for a Heinz ketchup factory, and the amounts which go in the bottle of ketchup are supposed to be normally distributed with mean 36 ounces and standard deviation 0.11 ounces. So once every 30 minutes, a bottle is selected from the production line and its contents are noted precisely. If the amount of ketchup in the bottle is below 35.8 or above 36.2 ounces, then the bottle fails the quality control inspection. What percent of bottles have less than 35.8? So here we have a range of values for the control, but we start by looking at the lower level. So let's look at that. So let X will be my random variable, which is the amount of ketchup filled up in the bottle, which actually distributes normal with mu 36 and sigma 0.11. Everything in ounces, right? So pay attention if you are dealing with the same units. So this will look like this. You have 36 in the center and then 35.8 on the left. So you are interested in what will be less than that. So this will be the left tail. At this point, what you can do is just calculate your z-score with that specific value minus the mean over the standard deviation, and then you get this standardized score. With that value, you go to either to R, right? And you can either give it the z-score value, or you give the row value and modify the mean and the standard deviation, and you should get the same results. So from there, let's say that what percent of bottles actually pass the quality control inspection. So let's remember, if the amount of ketchup in the bottle is below 35.8 or above 36.2, then we need to check two ends of the tails. So basically we want to check how many I have, or what percentage of bottles I do have in here contained. So I need to measure, I already measured this tail, I need to measure this tail and subtract it from 1, or either get the cumulative tail here and remove the tail that I already checked. So that's exactly the strategy that we're gonna use. So I'm gonna calculate this huge portion and then remove the little tail that I already calculated. So if I, this was my previous one, then let's say for the next point, 36.2, actually, I calculate my other score, and it's also 1.82, but now it's positive. So these were symmetric type of limits. So the probability of X being in between these two values is equal to the probability of my z-score being between these two. So I calculate my cumulative probability till 1.82 positive, which is 0.96, and I remove the probability of the little tail from before, which makes up 0.9312, which in real concepts is 93.12% of the bottles pass the quality control inspection. So you can also move backwards with this type of calculation. So let's say, for example, that body temperatures of healthy humans are distributed nearly normally with mean 98.2 Fahrenheit, and standard deviation 0.73 Fahrenheit. So what will be the cutoff for the lowest 3% of human body temperatures? So graphically, we know that we expect that little tail on the lowest edge of that distribution to contain 0.03 of all that probability. So, and my center is in 98.2 and my standard deviation is 0.73. So I ask first, so in order to get that probability, what should be my C-score? So with this, basically I will go to the actual table and check 0.03, where is it located and which values of C I have, or do I go to R and ask for that particular threshold? So once I find that minus 1.88, then I can go backwards and come from C to X, because that's my variable of interest. So my X will be 96.8 Fahrenheit. So this is the R command for getting that particular threshold. So this Q norm will receive the percentage of area that you want to check, and it will give you the threshold value for that contains that probability. So now we want to check the cutoff for the highest 10% of the human body temperatures. So now we go to the other end. So this tail corresponds to 0.10, therefore the lower part of it corresponds to 0.90. So we can do the same now, but we start with 90, because remember that we always look at percentiles to the left. So once you pay attention to that 0.90, then you can use what you know from probability to calculate the rest. So basically this is what you did, right? So you have the 0.10 and you know that all of these sums up to 1, then this one should be 0.90. So you find that 0.28, and that gives you an X of 99.1. So in terms of probability plots, you might find some of them, and you need to be prepared to interpret them accordingly, right? So for example, in this case, the histogram actually looks not that necessarily normal, right? Actually, this tail has a lot of observations that I might have not expected. So and it's actually makes sense, because this is a plot for NBA heights. So even though this tail is kind of like more or less the same, it's all located of course around 80 or something, but I have like a lot of outliers around here. So this is how my normal probability plot looks like, and as you can see, there is a strong tail here that deviates from the straight line. Therefore, I have some evidence that this distribution is potentially not normal. And there are formal tests that you can run to check this, and we will cover those when the time comes. But this is graphically how you can keep moving with assessing those type of things. So let's do another couple of checkpoints here. If birth weights in a population are normally distributed with a mean of 109 ounces and a standard deviation of 13 ounces, what is the probability of obtaining a birth weight of 141 ounces or heavier when sampling birth records at random? So this is our center, this is our standard deviation, and this is our threshold that we want to check. So how much of them, what's the probability that falls in this tail 140 after 141? So I get the C-score 2.46, and we can either find it in the table, right? So we first find the integer and the first decimal, and then the second decimal 0.06. So the sum of these two give me 2.46. This is my probability, 0.993. And then, of course, because I'm interested on this end, then I need to make sure that I get the complement of it, right? So this is the probability of everything to be at or below that level. Therefore, I need to subtract that to 1 to know what is on top of that. So this is how it will be calculated in R. If birth weights in a population follow that same distribution, what is the chance of obtaining a birth weight of 120 ounces or lighter? So you have the same distribution, but now you want to locate yourself in 120 and check everything below that. So same thing, we're going to calculate the z-score. 0.85 is located in this row, in this column, so we check 0.8023. So that is our probability, because we are caring about everything lighter or up to that point. And in R, we will calculate it this way. So 80.23% is the chance of getting a birth weight of 120 ounces or lighter. So just as a reminder, remember that in order to actually perform the z-score method and this standardization, you actually need to have quite symmetric distributions. If you don't have a really distributions that look symmetric, then your results will not be reliable. So you better pay attention to that and not just like run z-scores in the normal type of probability analysis with any distribution. That's why we are getting familiarized with a ton of different distributions, so you can question yourself first, is this the correct distribution, and then move with your analysis. So this is a reminder of your learning objectives. You had a couple of examples to practice. Make sure that you review them again if you still have questions. Check your understanding through taking the quiz.